How are you all doing this morning? So 2 of the 10 of you are here and tired and doing well. Nobody's willing to speak aloud, and that's okay. So today we are going to talk more about MOSFET biasing circuits and then move into MOSFET amplifier circuits. But before we do that, because we're getting towards the end of the quarter, I wanted to go ahead and introduce project number 3. So your third project, and you won't need to send me an email to pick which option you want because there's only 2 available, so I'll just let you do whichever you feel like doing, or your group, is to use a program called Electric VLSI. It is a design software package that is free to use, and it's used to create both analog and digital CMOS integrated circuits. It has lots of different configuration options and all that kind of jazz. The instructions for downloading it and installing it and setting it up are on Moodle. If you have any problems, I teach using Electric in the senior level class on integrated circuit design. So I'm very familiar with it, so I would be happy to help try to figure some things out. As part of the setup process, you are asked to effectively create an inverter circuit, which a former student made this one right here. This is a simple CMOS inverter circuit. Over here, you have an Nmos transistor, and over here you have a PMOS transistor, and they're wired up in such a way that if you put a positive input on the common gate terminal, you get out a 0 on the output terminal, and if you put in a 0 on the input terminal, you get a digital high on the output terminal, which is exactly how an inverter is supposed to work. Your task will be to use Electric VLSI to create either a NAND gate or a NOR gate. NAND and NOR gates are universal logic gates, and they're called that because they can be used exclusively to make every other logical function. So using just NAND gates or NOR gates, you can make AND or XOR, XAND, kind of the full gamut. So it's a pretty interesting topic, but some of them get wildly complex. Well, not wildly complex, but reasonably complex. The NAND gate and the NOR gate that you're being asked to create are simple 4 transistor circuits. There'll be 2 PMOS transistors and 2 NMOS transistors in each, and their architecture is almost identical. It's just whether you put the parallel combination on top or on bottom. Anyway, you'll see when you're doing a little bit of research for it. So this is your third and final design project. It is due at 5 p.m. on March the 2nd, which is literally the last minute of when the quarter is closing. So it's due the last day of the quarter at the end of classes. So let's see what we got in chat here. All right. So any questions with regards to design project number 3? Let's just use Electric VLSI to create a NAND gate or a NOR gate and do proper simulations as are necessary. All right, well, nobody's speaking up about anything, so I would highly encourage you to download Electric over the weekend and start playing around with it, trying to configure it and things like that. The hardest part of using Electric is getting it set up properly. So the earlier you start on that, the easier your life will be. All right, so let's get back to our analysis of transistor biasing scheme. So the next one that we're going to talk about is the self-biasing circuit. And the self-biasing transistor circuit looks something like this. We have a resistance RD placed between our drain terminal and our power supply. Then we're going to have a resistance RG placed between our gate terminal and our drain terminal. And we have some resistance RS placed between our source terminal and ground. All right. So this is a self-biasing circuit. It looks extraordinarily similar to the self-biasing BJT circuit. If we look at our large signal model for this guy, I'm going to start with, let's say, I'm going to put my gate right here. My resistor RS, this is my source. My drain current ID. Here's my drain terminal. Between my gate and my drain, I should have a resistance RG. And between my drain and my power supply, I have my resistance RD. And this is my voltage VS. All right, so a couple of things that we should be able to observe about this guy. So let's talk about number one. What is the relationship between the quantity VGS and the quantity VDS in this circuit? Anybody have any ideas? All right. This current right here, I'm sharing my screen, right? Everybody can hear me and see what the hell I'm doing. Yeah, okay. So this current right here that I've drawn in orange, what value is that current going to have? Not a trick question.
Should be VDD over RD minus ID.
VDD, I'm looking for a numerical answer. Let's see. Yeah, VDD over RD minus, let's try something different. Numerically, what value must that current have?
0 amps, I suppose.
Yeah, 0 amps, right? Because it's the current flowing through that gate resistance, which then sees the open circuit of the gate capacitance. So there's 0 amps of current flowing through my resistor RG, which means the voltage at this node and the voltage at this node are identical because there's no voltage drop over the resistor RG. Is that correct? So what I am positing is that since the current flowing through the resistor RG is 0 amps, the voltage drop over the resistor RG is 0 volts, which means the two nodes that I've circled have the exact same electrical potential. That means that VGS is exactly equal to VDS. What does this imply about the operational state of the transistor? Is it always off, always in triode, or always in saturation? Always in saturation, that's correct. So these self-biased circuits will always be in saturation. So we don't have to worry about accidentally entering the triode region or anything like that, because if VGS is equal to VDS, then VDS will always be greater than the quantity VGS minus the threshold voltage. It's literally impossible for that to not happen. All right, our second relationship that we can observe here is that our voltage Vs is simply ID times Rs. And our third relation then, VD is equal to VG, is simply VDD minus ID RD. So we now know what voltage we have at all of our different terminals, so we can develop our fundamental equations. All right, so VGS will be that voltage VD minus the voltage Vs. So that means we're going to have VDD minus ID times RD plus RS. Our drain current ID, because we are in saturation, will be 1/2 UN C ox W over L VDD minus ID RD plus RS, so that's just simply VGS minus VTH quantity squared. And with more algebra than I'm willing to waste time doing, we can rearrange this and we find that we have RD plus RS quantity squared ID squared minus 2 VDD minus VTH RS plus RD plus 1 divided by mu n C ox W over L times ID plus VDD minus VTH quantity squared is equal to 0. So we have another quadratic relationship where this guy RD plus RS quantity squared is A. This guy right here is B. And then this guy right here is C. So we could work an example to determine the operating point of a circuit without channel length modulation. So let's go ahead and do that. And our circuit will be this guy. And let's say that our transistor has an aspect ratio of 10/2. We'll be dealing with a threshold voltage of 0.4 volts. And mu n C ox is 200 microamps per volt squared. So with this in mind, our quantity A for our quadratic equation, RS plus RD quantity squared, comes out to be 6.25 times 10 to the 6 ohms squared. Our quantity B, which is -2 times VDD minus VTH, RD plus RS plus 1 over UN Cox W over L is negative -9 times 10 to the +3 volts squared per amp. And lastly, quantity C, which is simply VDD minus VTH squared, is 1.96 volts squared. So if we use our quadratic equation, we're going to get two results. ID1 is going to be when we have negative B plus the square root of B squared minus 4AC all over 2A. And I get 1.173 milliamps. And my current ID2 is negative B minus the square root B squared minus 4AC divided by 2A. and I get 267.452 microamps. And now we have a little bit of a situation. Both of these currents, based on our knowledge of transistor currents, seems reasonable in as much as they're both relatively small, right? Everything we've seen to this point suggests that our transistor currents will be somewhere on the order of a milliamp or smaller, which both of these are. Both of them are positive. So how do you guys suppose we are supposed to determine which of these is the correct answer? Any thoughts? So I hope that we can all agree from our large signal model that our drain current of ID is flowing through the 2 kilo ohm resistor, and none of it branches off to flow into the gate. And that same current ID is flowing through our 0.5 kilo ohm resistor. Right? And the potential difference between here and here is our voltage VGS, which is identical to the voltage VDS because we have a self-biased circuit. So with that in mind, we can determine the value for VGS. So I'm going to say VGS1 will be VDD minus ID1 times RS plus RD, and in doing so, I get a value of negative 1.131 volts. So if VGS were negative 1.131 volts, our transistor would not be in the saturation region, it would be off. So obviously this one is the incorrect answer. Down here, just for completion's sake, VGS2 will be VDD minus ID2 RS plus RD, and it would give us a value of positive 1.131 volts, which means VGS is greater than our threshold voltage, and therefore our transistor is on, so this must be our correct value for ID2. So that's how we can check our answers. If channel length modulation were included, let's circle back up to here to just kind of see what would be going on. So if channel length modulation were included, the only really changes that we would have to make would be including, let me put it. So we would have VGS is equal to VDS is equal to VDD minus ID times RD plus RS. So that one didn't change at all. Our second equation, ID, will be the exact same thing that we had. 1/2 UN C ox W over L, VGS minus VTH quantity squared, 1 plus lambda VGS or VDS, doesn't really matter. We could do a substitution in here and we'd find that we would have a third order polynomial in terms of ID that we would need to solve. And then we would have 3 different things that we would have to check, which to me is annoying. So I set up a MathCAD sheet to do this guy too, and I would suggest that you do the same. It will help you with at least one of your homework problems. All right. One last biasing scheme that you may see is what's called the diode connected MOSFET. The diode connected MOSFET is really just a special case of a self-biased MOSFET. So you may see something like this. Drain, gate, and source. And in this case, our large signal model is going to look something like this. Our gate and drain are shorted together, and they are both at our power supply voltage of VDD. So really all this is our self-biased circuit, except that RD and RG are both 0. And so we'll get the exact same equations. We just set RD and RG equal to 0. And so from this, our fundamental equations are VGS is equal to VDD minus ID RS, and ID is equal to 1/2 UN Cox W over L. VDD minus IDRS minus VTH on V squared, which gives us ID squared RS squared minus twice VDD minus VTH times RS plus 1 over UN Cox W over L times ID is equal to 0. We now can determine A, B, and C and figure out exactly what the operating point of this guy is. So from here, it's literally identical to what we did in the previous example. You won't see diode connected MOSFETs a lot in macro scale MOSFET circuits, but you will see diode connected MOSFETs where this resistor RS is probably going to be replaced with another transistor in integrated circuit architectures for the creation of reference voltages. So something that you're going to see potentially in 336, definitely in 438 if you choose to take the integrated circuit design class. We're going to look at an amplifier that's loaded with a diode connected MOSFET shortly, just to kind of get our feet wet in that area.
Dr. Hartman, the arrow pointing to that RS, what is that? Why is that pointing there?
So that's what I was just saying. You likely won't see that resistor RS actually there. What you would see instead is a MOSFET transistor in its place, so that the diode connected MOSFET, everything above this dashed line, might be connected to an amplifier circuit or something like that.
Okay, thank you.
Yep. All right, so speaking of amplifier circuits, let's get ready to rock and roll with our first one. So we're going to begin by talking about the common source amplifier, which is the MOSFET version of a common emitter amplifier. So our fundamental amplifier then is this guy. We have a resistance placed between the drain terminal and our power supply. And I want to point out here, fundamentally for all common source amplifiers, our input is applied at the gate terminal. Output taken at the drain. So if we have any circuit whose input is applied at the gate and the output is taken at the drain, that is a common source amplifier. I am flabbergasted how many of you guys missed that style of question on exam 2. That's how we determine all of these things. So common source means input is taken at the gate, output is taken at the drain. Then we'll have common drain amplifier, so the input will be applied at the gate, and the output will be taken at the source. And then we have a common gate amplifier where the input is applied at the source and the output is taken at the drain. It's all just permutations of where we're applying our input and output. So, anywho, our small signal model for this guy. And I'm going to work effectively all of these circuits with channel length modulation included. The textbook doesn't necessarily do that, but it's pretty easy to figure out what happens if you ignore channel length modulation, because you just set that resistance R naught to infinity and then see what falls out. So anyway, our small signal model is going to look something like this. So what we're doing, we are turning off our supply voltages. So that's why I've replaced VDD with ground. Here's where my AC input voltage is applied. And here's where my AC output voltage is set. Still the drain terminal, I've just moved it over to the left-hand side purely for space saving purposes. I'm going to label all of my terminals. So this is my drain, this is my source, and this is my gate. And so now, applying the small signal model, I have something that looks like this. Lowercase VGS because we are not looking at a DC circuit. Here is my source, grounded. BGS. My channel length modulation resistance are not. This is my drain terminal, and then between my drain and ground, I have that resistance RD, and my output voltage is between the drain terminal and ground, which is the same as the voltage over that guy there, and my input voltage plus all right. This error is going to keep popping up, so I'm going to save this real quick, close it out, and then reopen it. All right. So one thing that we're going to see for pretty much all of our MOSFET transistor amplifiers is that our input resistance is pretty easy to figure out. So who among you can remember what we did to determine input resistance for a BJT amplifier? Let's start there. So we literally spent weeks doing this. Nobody has any idea.
We divided our input voltage by our input current.
Okay, divide the input voltage by the input current. Perfect. All right, so I'm going to define my input current, current in orange, as this guy right here. So, right, that's the current flowing into my input terminal, and you're absolutely correct that my input resistance Rn will simply be the ratio of Dn divided by the current I have labeled as In. What is that going to be? So what is, let's see. 0. Okay, so if the current In by definition here must be 0 because it's the current flowing through an open circuit, right? So if we have some number, whatever the input voltage is, divided by 0, that means our input resistance is infinitely large. Effectively, we see the open circuit of the capacitor as our input resistance. This is technically only true for low frequencies. Now, low frequencies in this case can be on the order of in the kilohertz range or something like that. So as long as the signals that we're trying to amplify aren't very high frequency signals like radio signals and things like that, this is still going to behave effectively like an open circuit and will have infinite input impedance. All right, for our output impedance. I'm going to change the word resistance to impedance. How did we determine our output impedance? What did we do? What's the step that we have to take? All right. So anytime that we took our output impedance, we had to short circuit our input terminals. And then our output impedance was simply the ratio of that voltage V out, as if we had applied a test voltage source there, divided by, I guess it might be better if I draw a little source here. So I'm going to call this guy Vx. This guy is my current Ix. And the ratio of Vx divided by Ix gave me my output impedance. So with my input terminal for my gate shorted, RD times ID divided by R naught in parallel with RD. Okay, so RD times ID is voltage divided by resistance is current. So I'm confused as, are you telling me that my output impedance is that value, Vitali? All right. So you're partially right. The units tell me that you're incorrect. Like I said, RD times ID is a voltage. Voltage divided by resistance gives me current. The output resistance obviously is not a current. So if Vn is 0, what's VGS in this case? Zero, okay. So if VGS is 0, how much current is flowing through this source? Zero amp, all right. So what that test voltage source applied at the output terminal sees then is that resistance RD in parallel with that resistance R naught. So that's why Vitali was partially correct. R out is simply R naught in parallel with RD. So lastly, we need to calculate our voltage gain. Okay, so we're no longer shorting that guy. We're no longer applying a test voltage or anything like that. So I'm going to make a quick adjustment here that might make this a little easier to figure out. So what I'm going to do is I'm going to explicitly show that the resistance R naught is in parallel with the resistance RD. That's what I'm trying to do by putting this on ground. Okay. So it stands to reason that we can easily determine that V out is simply negative GM times R naught, excuse me, negative GM VGS times R naught in parallel with RD, right? Negative because the current is flowing into the negative terminal. So we're saying that this current flowing, so that current is flowing into this parallel combination of resistors. Maybe it's really smarter for me to draw this line that way. Doesn't particularly matter anyway. So R naught and RD are in parallel. The current is flowing into the negative polarity terminal and exiting the positive polarity terminal. So that's where this negative sign comes from. VGS in this case is exactly equal to V in. And from this, our voltage gain, AV, is simply negative GM times R naught in parallel with RD. So as a quick aside here, R naught is 1 over lambda ID. We have that from our small signal model equations, or at least R naught is approximately for this. So based on the size of the currents that we've seen and the values for lambda that we've seen, this would be something along the order of 1 over 0.1 times something like 250 microamps or so. Could be a little bit smaller, could be a little bit larger. Somebody do the math here and tell me what value R naught will approximately have based on these assumptions of 0.1 for lambda and a drain current of around 250 microamps. $40K. Yep. $40 kiloohms. Okay, so if our drain current were smaller, so if it were half, if the drain current were half the size, the resistance would be smaller or larger. Because 250 microamps is actually kind of large here, right? So since it's in the denominator, as this guy gets smaller, the output resistance should get larger, right? Or the resistance R naught should get larger. So what I'm getting at here is that this guy R naught is usually significantly larger than that resistance RD. Now, this is my preference because it's a more exact answer, but we could approximate it as negative GM RG, which is effectively what we would get if we had said that channeling, we are ignoring the effects of channel modulation. Now, what's interesting about this is assuming that we are in saturation, our voltage gain is then going to be negative the square root of 2 un C ox W over L times whatever value ID has. Terrible looking. And then outside of this guy, RD, or R naught in parallel with RD, which RD is smaller, makes R naught in parallel with RD look like RD. So we see that if ID and or RD goes up, AV also increases. Okay, so increasing our drain current causes our gain to go up. Increasing the value of RD also causes our gain to go up. However, it's also making that voltage drop go up, which is potentially causing our transistor to enter into the triode region. So in order for our transistor to remain in saturation, the product RD times ID has to be less than VDD minus VGS minus VTH. So if we want to increase our voltage gain, we have to ensure that our drain current goes down so that potentially so that we never exceed this constraint, which will cause us to go into the triode region. So we have a trade-off between the voltage gain of the system and what's called the headroom. Okay. Now we can actually mitigate this by a clever structure. Okay, so what if instead of having that resistor RD, we replaced it with current source? That type of circuit is going to look something like this. Goodness. VB here just stands for a particular bias voltage. I'm going to call this transistor M2. I'm going to take my output at the drain of transistor M1. And notice that the transistor on bottom is an Nmos and the transistor on top is a PMOS. So this terminal is the gate of transistor 1. This is the source of transistor 1. This is the drain of transistor 1. This is the drain of transistor 2, the gate of transistor 2, and finally the source of transistor 2. Because for a PMOS transistor, the source is always at a higher potential than the drain. Okay. So everything above the stashed line is effectively a current source applying some fixed amount of current, IB, based on that source gate voltage, VSG, for our PMOS transistor. So we're loading this guy with a current source, and we're going to be exploiting the large resistance of the current source to make our gain large and controllable effectively. So we're getting rid of some of, or we're mitigating that trade-off that we experience by putting a resistor there. So for our small signal model, what we are going to be drawing a small signal model on is this guy. So again, I'm just drawing the output voltage on the left-hand side for space saving reasons. Drawing the small signal model of this is a little bit complicated, so we're going to talk our way through it. The first thing I'm going to do, draw the small signal model for the Nmos transistor, because that's what we're more familiar with. So I'm going to start with my gate right here for transistor 1. VGS1. Here's my source. It's grounded. GM1, VGS1. This is my drain terminal of transistor 1, and here's where my output voltage is measured between the drain. So here's V1. So between V1 and ground is where my output voltage is. All right, for our PMOS transistor, I can see that the drain of my PMOS transistor, right here, is connected to the drain of my Nmos transistor. So this node is going to be V2. Between the drain of my PMOS and the source, I have that resistance R02. I have my dependent current source, GM2, VSG2, and it's VSG because it's a PMOS transistor. My source is connected to ground up here. And I'm going to draw my gate like this. So this is going to be G2. I'm drawing it down because the gate is at a lower potential than the source. And this guy is grounded so that this is my voltage plus minus VSG2. All right. So I'm sure that this looks very complicated to you because it looks very complicated to me. That being said, it's actually not that difficult to analyze if we make a couple of observations. So the first thing that I would like to think about is we can actually easily determine what that small signal voltage VSG2 is. Because on the positive polarity terminal of VSG2, we have ground. And on the negative polarity terminal of VSG2, we also have ground, which means VSG2 is simply 0 volts, which means this current source does nothing. It's an open circuit. And that vastly simplifies what's going on. All right. So with that in mind, let's determine our input impedance. Anybody have any ideas what that might be? Oh, and I never drew my input voltage. So make it in right here. All right, input impedance. Somebody tell me what's happening here. Infinity, absolutely right. So we still see the open circuit. So the input impedance is still infinitely large at low frequencies. Output impedance, arguably a little bit tougher. So I'm going to do something real quick here. Just drawing this line that's effectively bisecting this guy and separating the Nmos side from the PMOS side. So everything below that blue line looks exactly like our previous example, except that RD has been replaced by an open circuit. All right, Vitaly's got it already, okay? So what we are seeing then is VN is going to be shorted out, which makes VGS1 equal to 0, which means our dependent current source down here is going to be supplying 0 amps. So between this node, the drain, and ground, we see R01, but we also see that resistor R02 as well. And they're in parallel. So we can say that R out is R01 in parallel with R02. So a little bit more complicated. The advantage of this is that our output impedance is now going to be significantly larger, right? Because we saw that the channel length modulation resistance R0 is somewhere on the order of tens of kilo ohms usually, whereas our biasing resistors are usually on the order of just kilo ohms. So our output impedance has gone up, which should mean that our gain has also gone up. Our voltage gain for this system is simply going to be AV is equal to negative GM1 R01 in parallel with R02. So really all that we've done between the previous example and this example is we're using this MOSFET PMOS transistor to replace that resistance RD with a significantly larger value resistance, small signal resistance, which should therefore increase our voltage gain appreciably. but we won't run into the issues dipping into the triode region with a well-selected bias voltage VB. All right, let's see. We have 10 minutes left. The next one I want to talk about is what happens if we do a diode connected load. But I think that it's going to take more than 10 minutes to talk about. So I think that this is a pretty good stopping point for today. So class on Monday, I live way out here in Minden. I know right now the interstate is effectively closed between Monroe and Shreveport at this point because there's like 4 inches of ice still standing in some areas. I tried to drive just pretty much down the street, so like a mile to the Walmart here in town to pick up some sundry items, and they were closed. And I saw 2 cars get stuck on the way there because they don't have all-wheel drive like my car does. So I'm not leaving my house until all this ice crap clears up. So I will send you an email on Sunday evening to let you know whether or not I intend to actually show up to campus, but I would count on class being held over Zoom again on Monday until all this jibber jabber outside falls out. So that sound like a plan? All right, good. Okay, so thank you, Ronnie. All you guys stay safe as well. I extended the due date. I'm sure most of you got the email because those of you who hadn't selected a project and all that kind of stuff applied. But I have extended the due date of your second project until Tuesday. There was also that bonus project thing where I'm allowing everybody to redo a new project 1. So if you chose a voltage regulator, then you need to do a logic circuit or a rectifier circuit or whatever. That is going to be due also at the very end of the quarter, so that you have 10 days or some such nonsense to figure that out. So just be aware you have project 2 to get finished up over the weekend, and then a bonus project 1 if you need the bonus points for exam 1, and a lot of you do, and project 3 to be taken care of before the quarter finishes. So there's a lot of things that are going to require effort on your part in this class in the next week and a half until the quarter finishes. So I just want to make you aware of it so that you're not blindsided by anything. We're also going to have our final exam, I believe, is scheduled for Monday, March the 1st, that evening. I need to double check with Dr. Bakari on that, but I believe that's when it's scheduled. So lots of things happening in the next week to 10 days or so. So just keep that on your mind. All right, you guys have a great weekend. Stay safe, stay inside if at all possible, because it's real cold out. And I'll see you guys probably virtually on Monday and in class as soon as possible. All right, thank you guys.